So this is just an introduction to a couple of terms when we're dealing with acids and what acids are. Acids generally have the format of HA. And what that means is they're a hydrogen and some sort of an anion. Okay, so you have hydrogen with a chloride, which is hydrochloric acid, okay, or hydrobromic or hydroiodic, in which case the anion is an I minus, or it could be a polyatomic anion like a nitrate or sulfate or chlorate or perchlorate. Now the 7 acids that I listed above here are considered strong acids, and what that means is when you put these molecules into water, and by the way, they're not considered acids until they are actually in water, so HCl would be called hydrogen chloride. When they get into water, they completely ionize, except for this one right here, because this is a special one. It's a diprotic acid, and the first hydrogen completely ionizes, the second one incompletely. This will be an important exception to the rule for our strong acids, but we'll hit that one later. Okay? Now when this acid or this substance goes into water, it behaves in a certain way. What it will do is it will give up its hydrogen and will become HCO plus, leaving behind the anion A minus, whatever it is. So that would be a chloride or a nitrate or what have you. What makes a strong acid is not its concentrations. So don't conflate the two terms. You could have a concentrated strong acid. You can have a dilute strong acid. What makes a strong acid is when you figure out what the Ka for these guys is. Okay, I'm putting little AQs next to this. And the L is really important here. The Ka is basically equilibrium for acids. And they always have sort of the same equation because acids always do the same thing. So you're going to have HA, whatever it is on the bottom, and on the top you're going to have the H3O plus, or the H plus is how it's sometimes written. So recognize that these things, this and this, are kind of interchangeable. Okay? We know it's attached to the water. We don't always have to write it as attached to the water. And times the A minus. All right? And for a strong acid, the Ka is going to be large. Matter of fact, for any of these acids, if you look them up in a textbook, they won't even give you a value. They'll just say large or very large, which means there's a lot of product here. Okay? Which means the equilibrium point, the point at equilibrium, is very far to the right. Okay? And that's the hallmark of strong acid. When they go into the water, they cease to exist. Now, a term I'm going to use over and over again is survival of the weakest. Okay? And what that means is, you know, what survives in this equilibrium, this is very large because there's a lot of this. These are the weak guys. This and this are the strong guys, particularly this guy over here, the strong acid. Okay, now you could have a 1 molar solution, or a 0.01, or a 10 to the minus 6 molar solution. In all three of those cases, you still have a strong acid. So a 1 molar solution of HCl, okay, is a relatively concentrated solution of a strong acid. 10 to the minus 6 molar has basically less mole, it's moles per liter. So a 10 to the minus 6 molar solution of HCl is still a strong acid, but it would be considered, relatively speaking, dilute. And dilute and concentrated are relative terms, so that's why I have to attach numbers to them. So we'll say this solution here is more dilute than this solution here, which is more dilute than this solution there. And this, of the 3 solutions over here, this one is the most concentrated. Okay, so concentrated is a relative term. Strong or weak acid is not is a term that's they absolutely defined. Like these are the strong acids, or these are the weak acids. So let's talk about the difference between a strong acid and a weak acid. So a weak acid is like this acid. And I keep using this one as an example, but there's a lot of weak acids, and you're going to get a table to work from with those weak acids. And if you look at the Ka's for those guys, all right, the Ka for those acids is going to be usually is going to be a number of something times 10 to the negative something. The strongest weak acids have values of like 10 to the minus 2. A lot of them have values of 10 to the minus 5, 8, 9, 10, 11, things like that. Okay, vinegar or acetic acid, which is what this one is, has a value of 1.8, okay, times 10 to the minus 5. Now what that means is, assuming we have the AQs here again, right? AQ. If we have our, this is our weak acid, and that's equal to 10 to the minus 5, that means the value of the H plus concentration times the acid to the anion. In this case, this is your A, this is your anion, right? Make sure because that's not standing for acid, right? That's standing for anion. Really important distinction here, okay? So A minus is the anion, not the acid, okay? over the original acid, which was, HA, or, alternatively writing this, you'd write out the whole thing, be like, H3O plus times C2H3O2 minus over bracket HC2H3O2. The important point about this is, in this particular case, there's a lot more reactants, okay? And again, survival of the weakest. What this means is, if we think about like maybe 1 in 1,000 or 1 in 10,000, it varies with concentration. We'll talk about that soon. But only a small fraction of the vinegar molecules are going to ionize. Remember, I'm using that word not dissociate because they don't start as ions. They start as a covalently bonded molecular substance. But a small fraction of them will actually ionize and form acid. So even if I had, let's say, a 2 molar solution of vinegar, right, that would be a pretty concentrated solution, right? But still be a weak acid.